In the last module, we learned about variation method. Now, variation method, as I told you earlier, is an approximate method. Now, we shall apply the variation method to solve two simple cases. One is that of particle in a one-dimension box, and the other is the equation for helium atom. So, what we do, we write first of all the Hamiltonian for the system and then choose an approximate wave function, and using this approximate wave function we calculate the energy of the system, which by variation theorem we know is greater than the actual value of the energy E0. So, we first of all apply this to a very simple problem, that is a particle in a one-dimensional box. Now, the boundary condition of the problems are known, that the wave function has to be 0 both when x is 0 and when x is L. If we choose the approximate wave function phi a equal to x into L minus x, then it can be seen that when x is 0, the function is 0. When x is equal to L, again the function is 0. So, this satisfies both the boundary conditions. Now, use this approximate wave function to solve the Schrodinger equation. The Hamiltonian for this system is very simple, as there is no potential energy, so it has only the kinetic energy term. Now, writing the expression for the energy, we obtain this expression, and when we solve this equation, we note that this gives us energy equal to 1.014 h square over 8 ml square, where we know when we exactly solve this equation, Schrodinger equation for this problem, we find that energy, ground state energy, is equal to h square 8 ml. One thing we note, that EA is greater than E0, but the value is not so bad. There is a reasonable agreement between the, and we also obtain the wave function as x into L minus x. Now, applying it to a more complex system, we choose the helium atom. Now, helium atom, the problem is you have the nucleus, the electron 1 and electron 2. The complication in the helium Hamiltonian arises due to repulsion between electron 1 and 2, making the Hamiltonian, which has the kinetic energy part of the 2 electrons and potential energy of the electrons with the nucleus and potential energy of the repulsion between the 2 electrons. If the nucleus is very heavy, we can neglect the kinetic energy of the nucleus, and we write the Schrodinger equation simply like this. Now, we have the Hamiltonian, exact Hamiltonian, but now the problem is, what is the wave function that we must choose? For this purpose, we take a guidance from hydrogen atom, and we write the approximate wave function as, the only thing is we choose the charge as an unknown adjustable parameter and go ahead with the solution of the Schrodinger equation with this approximate wave function. Now, the Schrodinger equation now with this approximate wave function becomes like this, and this if you keep on solving this thing, we obtain energy is equal to this integral with the Hamiltonian and the approximate wave function integrating over the volume elements of electron 1 and electron 2. This gives us E is equal to z square minus 27 8 of z. Now, minimizing the energy with respect to z, we find that differentiating this with respect to z and then putting that equal to 0 gives us z equal to 27 over 16. That is, the charge of the nucleus is reduced from 2 to 27 over 16. This is because one electron provides screening to the other electron, and therefore it is physically a reasonable wave function. Energy that we obtain is equal to this thing, and therefore you notice that the energy obtained here is slightly higher than the real value of this thing. Actually, the real value of the energy is minus 79.00 electron volt, but with the approximate value it is 77.5 electron. So with one we have nearly 2% discrepancy between the real value of the energy and the approximate energy we have obtained. Go ahead with the determination of the energy. Simultaneously we are able to obtain the wave function also, approximate wave function also, from where we can calculate other properties of the system. Now, we can say that variation method is an approximate method, but it is quite useful, and we can obtain the value of the energy near to the ground state, and also we are able to obtain the wave function also, and their accuracies can be increased by choosing a larger number of adjustable parameters.
Now we will be studying the introduced concepts in detailed manner. After studying this module, you shall be able to write Schrödinger equation for complex system using variation method and solve Schrödinger equation for helium atom using variation method. As we are already aware that variation method is an approximate approach used in quantum mechanics to find eigenstates and eigenvalues of complex systems, let us now quickly look at how the variation method is used to solve the complex problems. The basic principle of variation method is to guess a trial wave function for the problem, which consists of some adjustable parameters called variational parameters. These variational parameters are fixed to minimize the energy of trial wave function. The resulting trial wave function and the corresponding energy are variation method approximations to exact wave function and energy. Variation method calculates an upper bound EA to the ground state energy E naught by using any appropriate guess or trial function psi A, where approximate energy is calculated as, in numerator, integral of psi A star into exact Hamiltonian into psi A d tau upon, in denominator, integral of psi A star into psi A d tau. The most important step for solving eigenvalues of complex systems using variation method is choosing or guessing the right guess or trial function psi A, which determines the success of variation method. The closer psi A is to psi naught, that is the ground state wave function, more closer EA, that is the approximate energy, is to E naught, that is ground state energy. A trial wave function can be taken as a linear combination of n linearly independent functions as given in equation 2, where an refers to the variational parameters. So, psi a, that is the approximate function, can be expressed as linear combination of orthonormal sets of functions psi n. The trial function so chosen must satisfy the same boundary conditions as the exact wave function and should be normalized. Moving further, we now study the simplest application of variation method, that is, let us try to solve the case of a particle in a one-dimensional box using variation method. Consider a trial function for the given problem as given in equation 3, that is psi a is equal to x into L minus x, where the lower and upper bounds for x are 0 to L, that is the length of the box. The trial function so considered here contains no variational parameter, but if the trial wave function would have been as in equation 3a, then coefficient k would have represented the variational parameter in the equation. The Hamiltonian for the particle in a one-dimensional box is as given by equation 4. That is, the exact Hamiltonian h naught is equal to minus h square upon 8 pi square m into d by dx, where m is the mass of the particle. Substituting the trial function as given in equation 3 and Hamiltonian from equation 4 into equation 1 to calculate approximate energy gives equation 5, where in numerator we have integral x into L minus x into minus h square upon 8 pi square m into d square by dx square into x into L minus x into dx upon, in denominator we have integral x into L minus x into x into L minus x dx, which on integration gives 2h square upon 8 pi square m into L to the power 3 by 6 upon L to the power 5 upon 30, which on simplification gives 10 by pi square into h square upon 8 ml square, or one can say approximate energy EA is equal to 1.014 into h square upon 8 ml square as given in equation 6. For the problem of particle in a one-dimensional box, the exact ground state energy is known to be of the form that is shown in equation 7, which is n square into h square upon 8 ml square, where for ground state n is equal to 1. Comparing equation 6, that is 1.014 into h square upon 8 ml square, with equation 7, which is h square upon 8 ml square, shows that the approximate energy EA is greater than ground state energy E naught as shown in equation 8. This proves that the variation method calculates an upper bound to ground state energy by using appropriate trial function. Over here, for the problem of particle in one-dimensional box, we already knew the exact energy expression, and therefore taking this as reference, we calculated approximate energy using a guess function to prove that variation method provides an upper bound to ground state energy. However, for various complex problems, exact solution of the Schrödinger equation is not possible. Therefore, we use variation method to calculate approximate energy using a guess function. Let us now move further to the system of helium atom, which is a three-body problem, that is, 2 electrons and 1 nucleus, for which the eigenstates and eigenvalues cannot be obtained exactly. Therefore, here we apply variation method to calculate approximate energy for helium atom. The helium atom has 2 electrons with coordinates r1 and r2 with respect to nucleus, which carries plus 2e charge, that is Z is equal to 2. The Schrödinger equation for helium atom is given in equation 9, that is minus h square upon 8 pi square me, where me is the mass of electron, into delta E1 square plus delta E2 square, where E1 and E2 refer to electron 1 and 2, minus h square upon 8 pi square mn, where mn is the mass of the nucleus, into delta n square minus 2e square upon 4 pi epsilon naught into r1 for electron 1, minus 2e square upon 4 pi epsilon naught r2 for electron 2, plus e square upon 4 pi epsilon naught r12. That is the interelectronic term. So again, Me is the electronic mass, Mn is the mass of nucleus, delta n is the Laplacian operator with respect to position of nucleus, delta E is the Laplacian operator with respect to electronic coordinates of two respective electrons present in the system. The first term gives the kinetic energy of electron 1 and 2 respectively. The second term is the kinetic energy expression for the nucleus. The third term gives the potential energy for electron 1 and nucleus. The fourth term gives the potential energy for electron 2 and nucleus. And finally, the fifth term gives the potential energy of electron 1 and electron 2, that is interelectronic repulsion. Further, to simplify this three-body problem, the nucleus is considered fixed at origin, as mass of nucleus is much greater than the mass of electron, which reduces the Schrödinger equation for helium atom to equation 10, where the second term of equation 9 is neglected and the Hamiltonian becomes minus h square upon 8 pi square me into delta E1 square plus delta E2 square minus 2e square upon 4 pi epsilon naught r1 minus 2e square upon 4 pi epsilon naught r2 plus e square upon 4 pi epsilon naught r12. In atomic units, equation 10 modifies to equation 11, that is, the exact Hamiltonian for helium atom problem becomes minus 1 by 2 delta E1 square minus 1 by 2 delta E2 square minus 2 by R1 minus 2 by R2 plus 1 by R12. Let the trial function be of the form as given in equation 12, where the trial function is expressed in terms of both the space coordinates r1 and r2 as z cube by pi into e to the power minus z r1 plus r2, where z is an adjustable parameter. If we now consider for one electron system like hydrogen atom or helium ion, wave function is known to be of the form as shown in equation 13. Psi is equal to z cube upon pi under root into e to the power minus zr by a naught, where a naught is Bohr's radius and z is the charge on the nucleus. With this, equation 11 gets simplified as given in equation 14, that is, Hamiltonian for helium atom becomes minus 1 by 2 delta E1 square minus z by R1 minus 1 by 2 delta E2 square minus z by R2 minus z minus 2 by R1 minus z minus 2 by R2 plus 1 by R12, where one electron Schrödinger function h psi is equal to E psi can be written as in equation 15, that is, minus 1 by 2 delta square minus z by r into one electron wave function, that is, under root z cube by pi into e to the power minus zr is equal to minus z square by 2 into under the root z cube by pi into e to the power minus zr. The approximate energy for this problem is then calculated using the expression as in equation 16, where exact Hamiltonian is given by equation 14 and trial function is given by equation 13. Substituting the trial function and Hamiltonian in equation 16 gives us equation 16a for approximate energy, which is EA equals to z to the power 6 by pi square into double integral e to the power minus z into r1 plus r2 into minus 1 by 2 delta E1 square minus z by R1 minus 1 by 2 delta E2 square minus z by R2 minus z minus 2 by R1 minus z minus 2 by R2 plus 1 by R12 into e to the power minus z into R1 plus R2 dr1 dr2. This on integration gives equation 17, that is the simplified expression for energy, which is equal to z square minus 27 by 8 z. As it is already known that z is an adjustable variation parameter, now in order to minimize the approximate energy, equation 17, that is the approximate energy, is differentiated with respect to z and equated to 0. That is, we now differentiate EA with respect to Z and equate this to 0. Del EA by del Z is equal to 0, which gives equation 18. Z minimum equal to 27 by 16. Also, we know that helium atom is a 2 electron 3 body system, while hydrogen is a 1 electron 2 body system. But if we ignore the inter-electronic interaction in helium atom, the ground state wave function for helium atom can be taken as product of individual electron wave function. That is, it can be approximated as product of individual hydrogen-like 1 electron wave function as shown in equation 19. Psi naught is equal to psi 1 r1 into psi 2 r2. Since energy is an additive property, it means on ignoring interelectronic repulsion, helium atom energy becomes sum of energy of two hydrogen atoms. The energy of hydrogen atom is given by equation 19a with Z is equal to 1. EH is equal to, in numerator, minus 2 pi square me z square e to the power 4, where E is the charge, upon, in denominator, n square h square into 4 pi epsilon naught whole square. So the helium atom energy now becomes as shown in equation 20a, minus, in numerator, 2 pi square me z square e to the power 4 upon n square h square into 4 pi epsilon naught whole square, minus, in numerator, 2 pi square me z square e to the power 4 upon, in denominator, n square h square into 4 pi epsilon naught whole square for each respective electron, which on simplification in terms of atomic units gives us expression 20 with n is equal to 1 for ground state. E helium is equal to minus z square upon n square, the expression that we have obtained on neglecting interelectronic repulsion term. Now substituting the value of Z minimum from equation 18, that is 27 by 16 into equation 20, gives us equation 21. That is, the approximate energy for helium is obtained as minus 2.8477 atomic units AU, or in electron volts as minus 77.5 electron volt. The experimental value of the helium atom energy is minus 2.9033 AU, or 79.00 electron volt. On comparing this energy with the variation approximate energy gives a result with 2% discrepancy. This result indicates that the variation method provides a fairly good route for solving complex quantum systems. Also, as we are already familiar that for helium atom the approximate energy obtained from perturbation theory is minus 74.83 electron volt, and the value that we have obtained just now from variation method is minus 77.5 electron volt. Comparing the results of perturbation theory and variation method with experimental energy value, which is 79.00 electron volt, brings to our notice that the variation method gives better results than perturbation theory. However, the bottom line of this discussion over efficiency of results obtained using perturbation theory and variation method is that the variation method is a robust technique in situations where it is hard to determine a good unperturbed Hamiltonian, while in cases where there is a good unperturbed Hamiltonian, perturbation theory can be more efficient than variation method. Let us now summarize the entire module. Variation method is an approximate approach used in quantum mechanics to find eigenstates and eigenvalues of complex systems. In this module, we applied variation method to particle in a one-dimensional box to prove that variation method provides an upper bound to ground state energy. From this, we concluded that variation method calculates an upper bound Ea to ground state energy E naught by using any appropriate guess or trial function psi a. The success rate of variation method depends on the choice of appropriate guess function. We then applied this approach to calculate approximate energy for helium atom. We obtained the approximate variation energy for helium atom as minus 77.5 electron volt, which is in 2% error with respect to experimental value, that is minus 79.00 electron volt.